Welcome back to Science Click. Today, the mathematics of general relativity, part 3, geodesics. In the previous videos, we have defined the concepts of world lines, motion as proper time goes by, and velocity, which indicates the direction in which an object moves through space and time. We would now like to describe the evolution of this velocity as proper time passes, in order to predict the shape of the trajectory. In our universe, objects naturally move in straight lines. When no force is applied, world lines tend to be straight through the dimensions of space and time. This comes from the symmetry of such a trajectory. An object has no reason to turn one way or the other. This simple consideration gives us a method to predict the trajectory of a body. As soon as we know its velocity at a given instant, we can just transport the arrow along itself to gradually predict the movement of the object. This type of trajectory, which is formed by transporting velocity along itself, is called a geodesic. In the universe, all objects tend to follow geodesics. On a geodesic, the vector does not turn. We can thus write that its derivative with respect to proper time is 0. Along the trajectory, the velocity vector of the apple does not vary. This equation simply says that the natural movement of bodies is non-accelerating, and therefore that when they experience no force, objects tend to move straight ahead. But we saw previously that the velocity vector can be written as the sum of its components multiplied by the basis vectors. Using this expression, and knowing that the derivative of a product is the sum of each term multiplied by the derivative of the other term, we obtain a relation between, on one side, the change in the components of the velocity, and on the other side, the change in the basis vectors themselves. The basis vectors can indeed vary throughout the trajectory, because the grid that we choose as our coordinate system can very well be irregular. Although the vector remains the same as a geometric object, its components on the grid can vary as the apple moves. When we think about it, the evolution of a basis vector along the world line can be decomposed as the sum of its evolution along each of the two coordinates, multiplied by the speed of the apple, because the faster the apple moves, the faster the basis vector will vary. For each coordinate, this gives us a new quantity which indicates how the basis vector varies along the coordinate. This variation is expressed as a vector, that is the derivative of the basis vector with respect to the coordinate in question. This vector is very interesting because it no longer depends on the trajectory, but only on the structure of the grid itself. This vector can be expressed through its components, denoted by the capital letter gamma. In our two-dimensional case, these components exist in 8 different versions, 2 components for 4 different vectors. These numbers are called Christoffel symbols. The Christoffel symbols are essential quantities for general relativity, because they encode how the grid changes along each direction. They contain crucial information on how our coordinates behave. Rewriting the previous equation using Christoffel symbols, we finally get to the geodesic equation. This very important equation allows us to calculate for each component of the velocity its rate of change as proper time passes. The geodesic equation thus allows us to predict the whole trajectory of an object, as long as we know its velocity at a given moment and the value of each Christoffel symbol all throughout the grid. To illustrate all these ideas, let's imagine not a space-time, but simply the surface of the Earth. We decide to use a latitude-longitude coordinate system, which at first glance seems to be a very good fit for the geometry. Now imagine that an airplane is moving in a straight line. When an object moves straight ahead without ever turning, its trajectory forms what is called a geodesic. In our situation, the geodesic is a great circle around the planet. On this geodesic trajectory, the airplane is always moving straight ahead. Its velocity vector does not change orientation. But when we plot the coordinates, the trajectory seems curved. The airplane seems to change orientation along the grid. In reality, its trajectory is perfectly straight. The problem does not come from the airplane, but from our grid. It's our coordinates that are curved. Their axes do not correspond to straight lines on a sphere. Compared to real straight lines, geodesics, they turn. Starting from a basis vector and transporting it along the grid, we can measure how much this vector changes by another vector. It's the components of this vector that are called Christoffel symbols. The Christoffel symbols measure the extent to which our coordinates deviate from straight lines along the grid.